Hello, everyone. Our research project was looking at applications of electrospun nanofibers, and the student researchers on this project are Kathleen Hesser, Tanner Marvitz, and myself, Christina Noel. And we worked under the mentorship of Dr. Smitha Rao in the Department of Biomedical Engineering here at Michigan Tech in Houghton, Michigan. So the recent COVID-19 pandemic exposed an American production supply chain unable to meet the tremendous demand for basic personal protective equipment, or PPE, including masks, gloves, and more. Rural areas across the country, such as the Keweenaw Bay Indian Community or the KBIC, were disproportionately affected by this pandemic, as resources were scarce and unaffordable in these regions. With new and existing viral respiratory illnesses on the rise in the last 15 years, access to basic PPE is more essential than ever before. This project aims to alleviate this strain by repurposing an electrospinner for use in filters for masks. An electrospinner is composed of a syringe pump, needle, voltage source, and a grounded collector, as you can see in Figure 1 here. The syringe pump pushes a polymer solvent solution out through the needle and forms a Taylor cone, where an electric field is applied to break the surface tension of the solution. This causes the solvent to evaporate and the polymer to solidify onto the collector, which is covered with aluminum foil prior to electrospinning to ensure that the fibers collected are removable. All of these components, including voltage, needle size, flow rate, distance from the collector, and rotation speed of the collector, can be modified to produce different sizes and alignments of nanofibers. These features can be characterized through the use of a field emission scanning electron microscope, or FESEM, dynamic mechanical analysis, or DMA, as well as ImageJ software. We specifically investigated how voltage would affect the production of the nanofibers to see if there is any relationship between the two that can be applied to produce filters for masks.
Varying voltage, we chose to vary it between 12 kilovolts, 15 kilovolts, and 18 kilovolts, keeping other parameters the same. As you can see in the data section, we have FESEM images for the 3 different samples, as well as directionality histograms for the 3 samples. Based on these results, the directionality histograms show a sharper bell curve with less deviation as voltage is increased. And this basically means that more of the nanofibers lay in the same direction during the electrospinning process as voltage increased. So directionality is also known as alignment, and the more aligned fibers were observed at the highest voltage, while the lower voltages had more of a mesh morphology. Another result of our experiment was the dynamic mechanical analysis. We got from the DMA a stress strain curve. The slope of the stress strain curve, or the Young's modulus, increased with increasing voltage. And this indicates that the stiffness of the fibers increases with the voltage increase used during the electrospinning process. The tensile strength was also increased with increasing voltage. So tensile strength is the point at which the fibers begin to break. Sample 1, the 12 kilovolt sample, fractured at around 0.5 megapascals. Sample 2, the 15 kilovolt sample, fractured at around 0.8 megapascals. And then sample 3, the 18 kilovolt sample, fractured at around 1.8 megapascals, seen in the DMA analysis. Now, we can conclude from this that all of these things, the voltage affected all of these characteristics of the nanofibers, and the strength of the electrospun nanofiber scaffolds can be changed by manipulating the voltage. However, even if a polymer nanofiber scaffold can be created that fits a precise need, they may not be affordable nor accessible to communities such as the KBIC, all while posing a significant environmental hazard. Nonetheless, there is a promise that there will be a way to efficiently make PPE for all communities in time, perhaps using natural fibers and other resources that are already available in the rural and indigenous communities. So an objective going forward is to research natural alternatives to producing PPE, such as silk protein or hemp, and to use electrospun, electrostatic nanofiber scaffolds for other research and design applications.
Over the course of these 8 weeks, our REU participants learned to fight our previous misconceptions and have an open mind to learn more about the KBIC, their background and history, and how it applies today. particularly as we're thinking about their access to masks and personal protective equipment. We were reminded that the members of the KBIC Ojibwe tribe are Anishinaabe, or original people, and were here long before the United States had been formed. We learned, for example, that treaty rights to hunt and fish in the Keweenaw were affirmed, not given, to the Ojibwe people by the US government. They had had those rights for millennia, but were not federally recognized until the 1700s, and then not reconfirmed until Supreme Court decisions as late as the 1970s. Neither researchers nor the government can give rights to a people. We also learned about the importance, especially in research, of asking respectfully for new knowledge. In Ojibwe culture, it is appropriate to offer a sema, or tobacco, to an elder when asking them where a plant grows or how to sew moccasin, any kind of knowledge or story. As we use our newfound research skills to help communities, it's important both to ask for assistance from the KBIC and others with knowledge about nature, and to truly listen to the information that they share. While we didn't know about the practice at the beginning of the program, we would like to offer a figurative gift of a sema to those who have supported us throughout the program, acknowledging particularly those at Michigan Tech, our mentors at the KBIC, and especially the National Science Foundation Award number 2050739. Thank you.